Hello friends, welcome to this video about partial sum approach in binary multiplication. The objective of this video is to explain a new binary multiplication method called the partial sum approach. This new method has the advantage to result in a simplified circuit hardware. As we learned from the previous video, one of the properties of the binary multiplication is that, in the worst case, a multiplication of two numbers of n bits generates a result which is made of 2 times n bits. As an example, let's see this worst case in the case of 4 bits. The highest number that can be represented with 4 bits is the number 1111, which is equal to decimal number 15. So the multiplication of 15 by 15 will give us the highest number we can get with 4 bits. So this is the multiplication. As you can see, the result takes 8 bits. This is the verification. The result is correct. And effectively, the result is made with 8 bits. So, what we learn from here is that if the multiplicand and the multiplier both are of n bits, at worst case, the result will be made of 2 times n bits. This is the first important piece of information that is going to be used in the partial sum approach. The basic binary multiplication circuit is quite fast because during the multiplication it adds all the partial products simultaneously, but as we already said, uses a lot of hardware because it has to add so many partial products together. In practice, old applications do not require such fast multiplier, and in some applications, the same multiplication circuit can also be implemented using less hardware. This is the aim of the partial sum approach. This method uses 2 tricks. The first trick of the method is that instead of adding all the partial products together simultaneously, we add only 2 partial products at a time. The addition of 2 partial products is called the partial sum. The second trick of the method is that instead of shifting the partial product to the left, we shift the partial sum to the right, and the partial product is kept at a fixed position. Let's visualize these 2 tricks with an example using 4 bits. The multiplicand is 1010, which in decimal is equal to 10. The multiplier is 0110, which in decimal is equal to 6. This is the multiplication process. This first line is just to set the number of bits of the result. If we start multiplying, this is the first partial product that we align to the left. This is the first partial sum. And here we shift the partial sum to the right 1 place and drop the push bit. This is the second partial product that we keep fixed in the same position. We add this, and this is the second partial sum. And here we shift again the partial sum to the right 1 place and drop the push bit, and so on. So we keep the partial products as a fixed position. We shift the partial sums to the right, and we add only two partial sum and products at a time. This is the result of the multiplication. This is the verification, and the result is correct. This table summarizes the rules that we have just applied. So note that using this process we only perform two types of operation: right shift and add. We make a right shift at every step, but we only need to add when the bit of the multiplier is 1, because when the bit of the multiplier is 0, there is no need to add, because the number plus 0 is the same number. So the number of operations has been reduced. The number of right shifts is equal to the number of bits, but the number of additions is only equal to the number of ones in the multiplier. As a consequence, the advantage of this partial sum approach method is that it requires less hardware compared to the basic paper and pencil method, and although not so fast, it is very useful in applications where we have a space constraint. Let's see now how we can computerize this process. Imagine we create a register for the multiplicand, another for the multiplier, each one of n bits, and another of 2 times n bits that we will call the accumulator, where we will store the result of the partial sums. Suppose that initially the content of this accumulator is cleared and it is all set to 0. Suppose that we start the multiplication of m times q, and at every partial product that we obtain, we add the partial product to the content of the accumulator. Suppose that each partial product, that in fact is 0 or the multiplicand, is always aligned and added to the most significant bits of the accumulator. Then, following the partial sum approach methodology, at the end of the multiplication, the content of the accumulator will be equal to the final result of the multiplication. Let's see now an example of computer multiplication applying the partial sum approach rules. This is the rules table. This is the multiplicand, and this is the multiplier. These are the bits of the multiplier: 0, 1, 1, 0, 0, 1, 1, 0. This is the accumulator. Initially, the accumulator is empty. This is the first step. The bit of the multiplier is 0, so we do only a right shift. A right shift. This is the second step. The bit of the multiplier is 1, so we do an addition and a right shift. An addition and a right shift. This is the third step. The bit of the multiplier is 1, so we do an addition and a right shift. An addition and a right shift. And this is the fourth step. The bit of the multiplier is 0, so we do only a right shift. So the final result is 00111100. This is the verification. So the result is correct. Note that with this multiplication we needed only two additions. One addition, second addition, because the number of additions is always equal to the number of ones in the multiplier. Now let's see the same operations presented in another format. At first it may look to you more complicated, but it is the same. We show you to get used, because this is the format we will use in next videos. This is the same example as before. This is the multiplicand, this is the multiplier, and this is the accumulator. 4 bits, 4 bits, and 8 bits for the accumulator. Initially, the accumulator is set to 0. This is the first step. The bit of the multiplier is 0, so we do a right shift only. This is the second step. The bit of the multiplier is 1, so we do an addition and a right shift. This is the addition, and this is the right shift. This is the third step. The bit of the multiplier is 1, so we do an addition and a right shift. This is the addition, and this is the right shift. This is the fourth step. The bit of the multiplier is 0, so we do a right shift only. A right shift only. So the result of the multiplication is 00111100. This is the verification. The result is correct. Note that the process is finished when all the bits of the multiplier Q are checked. This is the flow diagram of the partial sum approach process. Let's explain it. This is the multiplicand and the multiplier. This is the accumulator, and these are the bits of the multiplier. And these are the number of iterations equal to the number of bits. In this comparison, if Q is equal to 1, we make the addition. If Q is equal to 0, we go directly to the right shift. And this is the iteration loop. When we reach the number of bits n, that's the end, and we stop. And this is the flow diagram converted into a hardware circuit. This is the accumulator, and this is the multiplier. Depending on the bit of the multiplier, the control unit makes directly the right shift, or first connects the other through the multiplexer. The multiplexer, depending on the control unit, if it is 0 or 1, selects either 0 or the multiplicand. And then the other adds the partial product into the accumulator. And finally, the final result is shown in the accumulator. As a summary, we can highlight the following points. The partial sum approach method checks only one bit of the multiplier during each iteration, and based on its value either performs a right shift or also add the multiplicand. This process is repeated until all the bits of the multiplier are checked. In this way, the number of right shifts are equal to the number of bits. But the number of additions is reduced to the number of ones in the multiplier. The advantage of this partial sum approach method is that it uses less hardware and efficiently reduces the number of additions. And although the method is not so fast, it is very useful in applications where there are space constraints. Also, in this session, the flow diagram and the hardware circuit of the partial sum approach has been presented. That's all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos.